We're beginning our unit on sequences and series, and today is just an introduction to sequences. So I'm starting with question 1, sketching the graph of f at x, which is equal to 2x plus 1, and that we should know from our grade 9 work. That is degree 1, and it will be a line, and we know that that line has a slope of 2 and a y-intercept of 1. So when we go to sketch that, we want the line to go through the y-axis at positive 1, and our slope is 2, so that means we're rising 2 and running 1, and it's positive, so our line should go up to the right. So if I plot these points, now for this one our domain is x is an element of the reals, which means we're including every single value along that pathway, and so our line should look something like this, and we can label that f at x is equal to 2x plus 1. And I have a really bad stylus here, and I need to get my other one out. Okay, part B is similar, except the domain is different this time. We're just working with the natural numbers, and we know the natural numbers are the ones we work with first. We learn first when we're learning our numbers. So they're the numbers like 1, 2, 3, and so on. They're the numbers we first learn when we're learning how to count. So if we look at our graph, we don't want to include any value of x except where x is 1. And for this function, if x is 1, let me just write that somewhere else because I want to put something else underneath. Let's say we have a table of values. I'm just going to put this in the middle here. When x is 1, we sub that in, our y value is 3. And we know that from the previous graph, that gives us a point right here. So this is just going to be a point, and we're not going to join things together because I can't use 1.5 or 1.25 or 2.375. We only have our values that are being natural numbers. So when x is 2, our y value ends up being 5. So that would go here. And if I had a bigger grid, I could then figure out when x is 3, I would have a value of 7, and so on. If I had a 4, we would have a value of 9. Okay, so our table of values looks something like that. Now, in terms of these two things, this first graph, we had what's called continuous data. Continuous data is the fact that we're joining all our values together here because with a solid line, because no value of x is actually being left out at all. It's continuous data. In our second example, because we are only looking at specific values, specific points, this is called discrete data. And if you go into data management for grade 12 math, you might look at the difference between continuous and discrete when you're working with your data management. All right, now these points aren't joined together because we are leaving values out. Now, in terms of what we could call this or look at, this table of values really could be written as a sequence of values. The first term was a 3. The second value, or the second point, had a y value of 5. The third one had a y value of 7. The fourth would have a y value of 9. And because it's the natural numbers, there's no upper limit to this, so I'm just going to put the 3 dots, which is called the ellipsis, which indicates this goes on forever. Okay, so continuous data and discrete data here. Now let's move on to the bottom of this where we start actually defining things. The first thing that we're going to define is what is meant by a sequence. Well, what I have written right here is a sequence of numbers. It's an ordered list of numbers, okay? And this first number right here is what we would call the first term of the sequence. And it's like the value, the first term, this is our term number here. This would be, sometimes we use the letter n to represent the term number, and this is the actual value of the term. So this would be term, actually let me put the arrow pointing to this. This would be term n in general here, and I'm just gonna erase that part. There we go. So this value here, we have when n is 1, our term 1 is equal to 3. So term 1 down here is equal to 3. When n is 2, so n is 2 in this spot, we would have term 2 being equal to 5, or right here, term 2 is equal to 5. So these little numbers here underneath or beside the t, those are subscripts. It's like when we did slope is equal to y2 minus y1, and that's just saying the y value from the second point minus the y value from the first point divided by the x value from the second point, subtract the x value from the first point. So those are subscripts, they're not exponents. Please do not make them exponents. All right, and then we have term 3 is equal to 7, and so on. Now, what eventually we want to do is be able to come up with an expression to represent term n, any term to this sequence, how we could generate that. So that's what we're going to get into with our next part of this. All right, our first thing we need to define is what a sequence is, and a sequence is just the ordered list of numbers. So up above we had the ordered list for our natural numbers. For that particular sequence we had the set of, so the curly brackets is just your set of the numbers, 3, 5, 7, 9, 11, and so on. And that was an infinite sequence because we had the ellipsis at the end. We didn't have a defining value saying that we stop at this particular point. Now, a term in the sequence is just one individual number in the sequence. So 3 is a term, or 5 is a term, or 7 is a term, or 9 is a term, or 11 is a term for this particular sequence. This is an example of an infinite sequence. An infinite sequence goes on forever. There is no last term to it. It just continues on. So I'm going to type that into here. So our infinite sequence has no last term. It goes on forever. You'll notice when you list it out, it has the 3 dots at the end, and that's called an ellipsis. Whereas a finite sequence has a last term. It has an ending point. So lots of our real life examples are finite sequences. For example, when we put our money in the bank, there is an end to the point where we keep that money in. Eventually, maybe we take that money out. So maybe it's only a span of 5 years. So we would only have 5 years worth of values in terms of our interest. Likewise, if we're counting the number of rows in a theater seating usually has shorter rows at the beginning and then it kind of spans out as you head towards the back. So your theater seating might look something like this, where you've got fewer rows or fewer seats in the front rows, but as you head towards the back, perhaps every row increases by two more seats, but eventually you get to the end and you would have a finite sequence in that case. So the seating in the theater, maybe there's 25 seats in the first row, and then the second row has 27 seats, and the third row maybe has 29 seats, and so on, up until you get to the last row, which maybe has, let's go with 39 seats, okay, small theater there. So that would be a finite sequence. Now, there's a couple different ways that we can express our sequences, and as I said, we would like to be able to come up with a general expression so that I say, well, how many seats are in the 11th row in this theater? I could just be able to figure it out right off the bat without having to actually list all 11 rows out. Now, there's 2 different ways we can express these. Not all sequences can be expressed with recursive formulas, and not all sequences can be expressed with general term formulas. Some can be expressed with both, but sometimes it's easier to express one in terms of one way versus the other. So a recursive formula, if you're into any kind of computer programming stuff, computers were designed to make tasks that were very repetitive much more efficient, so you don't have a human calculating the same thing over and over again. And to do that, it just keeps calling the same bunch of code up and reiterates it or goes through it over and over again, or it reoccurs, it calls itself up. So with a recursive formula, what it's doing is it's taking the previous value you had or previous values and creating the new value based on what the previous value was. So a new term is generated by performing mathematical operations with previous terms. Okay, so we'll look at some examples of that, how that works in with the examples that we had on the previous or the example that we had earlier on with the graph, a recursive formula always has two parts to it. And you need to remember this, that it's not just a single piece. Recursive have two parts. Okay, and the two parts look like this. I'm going to see if I can do this as a separate text box. Yep, it'll let me. So part A would be, you've got to plant the seed. You've got to have a starting value. So part A is the term, or sometimes you need more than one term, the term or terms it starts with. If you don't have a starting value, you can't actually come up with the next value. You don't know what you're doing to it mathematically to get to the next value. And then you have the formula. Okay, so we'll do the example that we had in terms of the graph that we used. So we had the sequence up above, the 3, 5, 7, 9, 11. So if we rewrite that out here, I'll just go through that again. If we have 3, 5, 7, 9, 11, and so on. What we have noticed here, you might notice that to get from 3 to 5, we're just adding 2. So we're just adding 2 here. And then to get from 5 to 7, we're just adding 2 again. And then from 7 to 9, we're adding 2 every time. Now, this is like our first differences. If you created this as your little table of values with your x and your y, when term 1 we had a value of 3, term 2 we have a value of 5, term 3 we have a value of 7, 4 we have a value of 9, and so on. These really are our first differences, and we know it's linear because we're adding the same amount every time. Now when we have a constant amount we're adding, or when it turns out to be a linear relationship, that is what we call an arithmetic sequence, and we're going to talk about these tomorrow, arithmetic sequence. Now, to come up with this then, I could say to get to my next term, I would just be adding 2 to the previous term, so performing a mathematical operation with the previous term. So really I'm taking my previous term and adding 2 to it. Okay, so what I want to come up with is a formula. I want to say that term n, so any term in the sequence, is just equal to the term before term n. The term before term n, so if I had term n down here, the term before it would be n take away 1. It's right before it. So this would be term n with a subscript, term t with a subscript of n take away 1. So this is saying take your term before it and add 2 to it to get the next term. Now, as I said, that's the formula piece, but you always have to plant the seed. You have to tell us what we're starting with. We know that term 1 has a value of 3. So there's my starting point. So I know that if term 1 is 3, then I can build term 2 by taking 3 and adding 2 to it. I can build term 3 by taking term 2 and adding 2 to it. Now, in general, if recursive is okay, except you really, like if you want the 100th term, you're going to need the 99th term, which means you need the 98th term, which means you need the 97th term, and so on, all the way back to 1, which is a lot of work generating all of those terms. So a general formula term, or general term formula, is much easier to work with. Now, I said this is a linear relationship, and we know the equation was given to us back on the previous slide or at the top of this page. And what we know is that my y-intercept, if I were to back this table up a little bit and put a 0 here, that will give me my y-intercept. And if I were to subtract 2 from 3, that gives me a 1. So there's my y-intercept there. So my general term could be written as 2 times my term number, 2 times, that's like my slope, 2n, and then plus my y-intercept, which is 1. So my slope and my y-intercept can get that. Now, sometimes you'll see this written in function notation, which will be t at n equals 2n plus 1. So I could get the 100th term very quickly by just doing t100 would equal 2 times 100 plus 1, and that will give me a value of 201. So my 100th term in this sequence would be 201. Hopefully that makes sense in terms of, little pun there, in terms of what we're doing. So if I take that general term here, my formula for my general term, if I were to put 4 into my equation, I would have 2 times 4, which is 8, plus 1 more, generates the value of 9 there. So it does work out. Now, in terms of a formula for this, a general term formula is just a term is generated by using a formula based on the term's position in the sequence. And I'm going to type that in down here underneath.